Got it. Thank you very much. Thank you to Joel, Avishai, and Colin for organizing another great workshop. It's so nice to be back in Santa Cruz. So what I want to discuss today is a single piece of a much larger story on the role that the CGM plays in regulating the mass budget of galaxies in the early universe. And so specifically, I'll share with you what we're learning about the nature of ram pressure stripping in Milky Way mass halos. And so there's an interesting story there. So we typically think of ram pressure stripping in the context of kind of more massive halos, those that host groups of galaxies or clusters. I'll show you that ram pressure plays an interesting role in these lower mass halos. So in the movie behind me, I'm showing you the formation history of a Milky Way mass disk galaxy from a set of simulations that I'll introduce in a second. On the right is the projection of the stars, and on the left is the projection of the gas. And so what I want you to take away from this movie are two things. We can't ignore the importance of satellite accretion when we're thinking about kind of the mass growth and structural evolution of these galaxies at early times. The second thing I want you to take away is the complicated density and velocity structure of the CGM immediately in the vicinity of the central galaxy. So that's going to come back to it's going to become important for the punchline of this talk. So the simulations that we'll be looking at are from this the foggy. Hopefully Molly and Jason aren't watching the live stream. They're from this foggy simulation suite. So the folks who have bigger heads here were really critical in getting these simulations off the ground, and then the rest of us peons are down here. You can see that there's a very cool logo. There's a lighthouse that spins around. So what's interesting about these simulations? So they're run with ENSO, which is an adaptive grid code. And so with adaptive grid codes, you get the choice of the scheme you want to use to assign resolution. And so the traditional way this is carried out is through something like a density-based refinement scheme where you assign resolution in areas of high density. And so what happens here is you end up assigning a lot of resolution to the dense ISM. So in this case, we have it at 100 parsec resolution. And you leave the CGM around galaxies at a coarse resolution, so something like in the 1 to 6 kpc range. We're interested in studying the CGM in detail. And so what's done with Foggy is we Fullstop Force a minimum resolution in a box that spans 100 kpc around the central galaxy. And so that resolution here is about 400 parsecs. And above that resolution, we allow it to refine twice more if the refinement is warranted by the density-based refinement scheme, or if that refinement will allow us to resolve the cooling length, which will let us capture kind of the interesting fragmentation physics. So everything in red and green here, the cooling length is resolved just by the nature of the setup of this problem. In black, admittedly, the cooling length is not necessarily resolved. We had a lot of discussion about this. But these simulations are at least in order of magnitude more resolved than what we would traditionally use as a scheme. So I could just show you what these look like. So on the left is the low resolution CGM run. These are the same exact. This is a box with the same initial conditions, the same physical models. The only difference is the refinement scheme that we're forcing. And you can see in the forced refinement high resolution CGM, you resolve out a lot more density contrast, right? And from the movie at the title slide, that you also resolve out a lot more velocity structure. So this is something that I was alluding to yesterday. These galaxies look different, right? Which is really interesting. You increase the resolution of the CGM, something happens to the central galaxy. The central galaxy has the same resolution. It's all governed by the density-based refinement. I would not look too much into this. As I said yesterday, if you rerun this simulation 4 times, the differences between these are actually negligible compared to that scatter. That was a sidetrack. The point to take away is that these simulations are resolving a lot of interesting, kind of messy structure in the CGM around these galaxies. And so here is a family photo of the 6 halos in foggy, and you can see the CGM is just, it's hard to even describe it. It's messy, it's chaotic. There's a lot of interesting density structure and velocity structure. I'll show you that in a second. So let's circle back to what I opened with. So I'm interested in exploring ram pressure in these halos. Just so we all remember, the ram pressure goes as the density of the fluid you're moving through, so the CGM in this case, times the relative velocity of the CGM and, let's say, a satellite moving through that halo squared, right? And so here is a plot of the 1D velocity of the fluid, the forward-facing velocity versus the gas density. These are lines of constant ram pressure where we're increasing ram pressure going this way, right? And so this is what the low-resolution CGM simulation looks like, and this is what the high-resolution CGM looks like. And so what we're doing is we're naturally recovering a larger spread in density and velocity. And so what happens here is like this is a volume-weighted distribution. So there's a lot more volume that is at high velocity, and that will contribute a lot more to the ram pressure. By the same token, there's a lot more volume at lower gas densities and lower velocities. So it's a trade-off. So the spread, the larger spread in density and velocity translates to a larger spread in ram pressure. And so here is the last few days of a satellite in our simulation. And you can see that there's a lot of stuff going on. The one frame of this movie that I really want to take away is this one right here, where you could very clearly see this galaxy being ram pressure stripped, and it's about 15 kpc from the center of the galaxy. And so the criteria so we want to ask ourselves, when is a gas parcel actually going to be removed from these satellites, right? They're experiencing ram pressure, but is it enough to overcome their gravitational binding force? So if the ram pressure is applied for a long enough time, you can use this Gunn-and-Gott criteria, which is that the ram pressure exceeds the gravitational anchoring force per area in the galaxy. What's more relevant to the ram pressure profiles that I'm about to show you is this criteria, which is more or less a generalization of this criteria. That is to say, if you integrate the ram pressure over time, this gives you a momentum surface density that's imparted onto a gas parcel. And if that overcomes the surface momentum that you need to escape, then the parcel will be removed. So this lets us kind of integrate a trajectory. So I'm going to do the most simple thing you could do with these simulations. I'm going to look at a random sample of radial trajectories starting at 100 kiloparsecs and just moving towards the centers of these galaxies. So here's one radial trajectory, here's another, here's another. So we'll start with this plot. On the vertical axis is the surface ram pressure as a function of the distance from the central galaxy. Here is one random radial trajectory from that simulation in the previous slide. And you notice a couple of things. The ram pressure is more or less constant from 100 to 25 kpc, and then ramps up below 25 kpc. Over the next 2 slides, I'm going to show you that there is a tremendous amount of variation that depends on the specific trajectory that we choose. So here's another trajectory through that same halo. The story here is a little different. So you get this constant ram pressure here, and it spikes up a little bit, and then it just plummets to nearly 0. Presumably, this entered a cavity of low density, low velocity gas. It hangs out there for a little bit. It pops back up, plummets again, and then finally pops back up here, right? And here's another random radial trajectory through that same exact halo. A satellite moving on this trajectory would not even know it's kind of encountering a CGM until it's about 40 kpc away from the center. So what I want you to take away is that there is a tremendous amount of variation in the surface ram pressure profiles depending on your line of sight trajectory. And so what we can do is draw 100 random trajectories through the halo and plot their median. So that's what we're doing here. And I want you to take away 3 things. There is significant trajectory by trajectory variation. It accounts for about a 2 dex difference in the surface ram pressure profile. At large distances from the centers, the ram pressure profile tends to be constant and low. And inside 25 kpc, there's a dramatic rapid rise. Okay? So this is the quantity. Now we're moving from ram pressure profiles to a test particle that we let drop at the free fall rate. Starting at 100 kpc, we're letting it drop through these trajectories. And this is the cumulative surface momentum that is imparted on that test particle. And what I want you to take away is this really dramatic rise right here in the final 50, 100 million years of this test particle, where most of the surface momentum, let me come back to that in a second. Most of the surface momentum, 95%, is imparted right at the final stages of this thing. And so one thing we can do, we can argue about these numbers, but I just want to illustrate this, is we could take satellites with a given distribution of mass and a given gas fraction and a effective radius, and we can ask the question, at what point is the ISM removed at distances larger than an effective radius? And those are these dashed lines here. And you could see that the momentum that's imparted in these last 50 million years is enough to remove the ISM in these toy galaxies beyond an effective radius, right? So this removing a substantial fraction of the gas. This is a general conclusion that comes out of all 6 halos, so I'm showing that here, that there's this constant kind of low ram pressure profile, and then right at the end, the final 25 kiloparsecs or so, it just ramps up, right? And so these would not show up as, you can imagine translating this into like a quenched fraction as a function of distance from the center. These things are quenching, their gas is being removed almost immediately before they merge with the central. So this doesn't, the implications for like, the fraction of galaxies that are quenched are not that strong, but this does have strong implications for the amount of mass and momentum that's deposited onto the central galaxy, right? If these things are actually losing a lot of mass right before they merge. So there's those 95%. Here are the 6 simulations. As a function of mass, total surface momentum imparted. Again, I want to stress that the trajectory, there's a 2 dex scatter from just the trajectory by trajectory variations. And that has to do with the kind of complex velocity and density structure that we're recovering in these simulations. And again, here are those kind of toy model lines that I drew earlier. And these variations are more or less on order what you'd expect for, one trajectory could remove the ISM beyond an effective radius in a 10 to the 10 solar mass halo in the same exact 10 to the 10 solar mass satellite. In the same exact halo, another trajectory can only remove it in a 10 to the 8, right? So there's a lot of stochastic variation that are coming out of these experiments. So the takeaways, what I want you to take away is that ram pressure stripping in 10 to the 12 solar mass halos, or redshift 2, we're finding that it can be stochastic, very large trajectory by trajectory variation. It's late acting, right? most of the surface momentum that's imparted is done so in only the last few tens of millions of years of free-fall trajectory, which is not a realistic orbit, by the way, right? This is like the most simplistic orbit of a satellite that you could think of, just something free-falling, not having any sort of second or third passage. But anyway, yes, so the majority of the total surface momentum is imparted in those last 25 kpc, and it's significant. So comparing with the toy models, in that last 25 kpc, the amount of momentum that's imparted can remove the ISM from reasonably massive satellite galaxies. Thank you very much. I appreciate your time.
Questions? Oh, it's always you two. Frank.
So you did an
Yeah.
experiment where you drop test particles in a potential and you just let them accelerate to the center and then you register the total accumulated
That's right.
momentum that's imparted. That ignores, though, the fact that at some point you will hit terminal velocity, that the ram pressure will actually decelerate you.
So the ram,
So I think,
yeah.
doesn't this dramatically overestimate the amount of momentum you impart? Because you don't.
I could think about that a little bit more, but so the ram pressure is not coupled to the stars. So the stars are still moving on this trajectory, and I guess of course the gas eventually, once it's stripped, it's because it's reaching some sort of terminal velocity, and the stars are just going to move on along their merry way. But I think if you think of this as a clump of stars that has some ISM moving on this free fall orbit, and whether or not the gas is eventually removed is, I think, another question. Is that satisfying?
I have this picture of this bow shot that created.
Yeah. Yeah.
But maybe you're right.
Neil, last question.
Mm-hmm.
And you're finding that it matches. But he found that that whole momentum transfer paradigm doesn't hold when you're not in the hydrodynamic limit, which doesn't, because you just take these situations like galaxy and gas, and he found that those non-hydrodynamic effects completely change the outcome, and that the standard grand pressure model doesn't actually hold. I don't get this comment.
Okay, I'll have to remind myself of those papers. I don't have any strong comment.
Okay, we're going to move on.
Yes.